the eigenvalue problem. In this section, we're going to talk about important topic of eigenvalue and eigenvector. A central question is, when A is an n by n matrix, do non-zero vectors like x in the n space exist such that A times x is a scalar multiple of x? The scalar, which denotes by the Greek letter lambda, is called eigenvalue of matrix A, and the non-zero vector x is called eigenvector of A corresponding to lambda. The origin of term eigenvalue and eigenvector are from German word Eigenwert, meaning proper value. So basically, when we are talking about eigenvalue and eigenvector, we're forming this equation, Ax equals to lambda x. Lambda is eigenvalue and x is the eigenvector. If lambda is positive, setting Ax equals to lambda x result in x, which is multiplied by lambda x. Lambda is just a number. You have a larger vector in the same direction. But if lambda is negative, you have a vector in the opposite direction. So you have vector x and lambda x is in the opposite direction. The definition of eigenvalue and eigenvector. Let A be an n by n matrix. A scalar lambda is an eigenvalue of matrix A, and there is a non-zero vector like x such that Ax can be written as lambda x. The vector x is an eigenvector of A corresponding to lambda. Well, suppose you have the following matrix. You have a 2 by 2 matrix, 2, 0, 0, and negative 1. Verify that this vector 1 and 0 is an eigenvector of A corresponding to eigenvalue 2. And the second vector 0 and 1 is an eigenvector of A corresponding to eigenvalue negative 1. It should be very easy. If you multiply x1 on the left by A, you have 2, 0, 0, negative 1 multiplied by 1 and 0. This is this vector just right here. So we are forming Ax. This guy is equal to 2 and 0, which is 2 times 1 and 0. So you basically formed lambda times x. So this is the same vector, x. This 2 is your lambda or eigenvalue. Now, since x1 is equal to 1 and 0, lambda equals to 2 is the eigenvalue corresponding to this vector, eigenvector. And then, if you multiply x2 on the left by A, here you have matrix A multiplied by second vector 0 and 1. It results 0 and negative 1. If you factor out negative 1, you have negative 1 times the same vector. So basically, you showed that if you multiply the vector by negative 1, it is the same as A times that vector. So we just verified that vector x2, 0, and 1 is an eigenvector for the eigenvalue negative 1. As easy as that. Now suppose you have this 3 by 3 matrix. Verify that x1 and x2 are eigenvectors of A and find their corresponding eigenvalues. Let us begin, everybody. By definition, you have eigenvector. If you multiply A by x, you can simplify it to lambda times the same x. So this is all you're trying to do, doing algebra. So Ax1 is just a multiplication of 3 by 3 matrix and this column, which is equal to, well, here you have 1 times negative 3 plus negative 2 times negative 1 plus 1, which is equal to 0. The second value is also 0. 0 times -3, 0 times -1, 0 times 1 is 0. The last row multiplied here, -3 times 0, 1, -1, 1 and 1 becomes 0. So if you factor out 0, you basically have 0 times the same vector, which was here. So the eigenvalue is equal to 0. The eigenvalue for the eigenvector -3, -1, and 1 is 0. We're going to do the same thing for the second vector. Ax2 is just a multiplication of matrix by x2, which is 1, 0, 0, which is 1, 0, 0. Here, if you multiply these two, find the dot product, 1 times 1 plus 0 is 1. This is going to be just 0, and then 0 times 1 plus 0 is also 0. So you can factor out 1. You get the exact same vector. What's the meaning of that? It means that vector x2, which is 1, 0, 0, has an eigenvalue 1 corresponds to it. In this theorem, we're going to form the eigenspace of lambda. If A is an n by n matrix with an eigenvalue lambda, then the set of all eigenvectors of lambda together with the 0 vector is a subspace of n space, and this is called the eigenspace of the eigenvalue lambda. So again, you're going to just take all eigenvectors that corresponds to lambda along with the 0 vector. And this is called the eigenspace of lambda. Suppose we try to find the eigenvalues and corresponding eigenspace of this matrix. You have a 2 by 2 matrix. Let us begin. Geometrically speaking, multiplying a vector like x and y in the plane by matrix A corresponds to a reflection in the y-axis. So if you take a vector x and y and multiply it by this matrix, you get this second vector -x and y. So we can verify that algebraically as well. -1, 0, 0, 1 times x and y gives you -x and y. Well, -1, 0, 0, 1 times x and 0 is equal to -x and 0. If you factor out -1, you create the same vector x and 0. So the eigenvalue is lambda equals to -1. Now for a vector on the y-axis, like 0 and y, -1, 0, 0 and 1 multiplied by 0 and y is equal to 0 and y, or just 1 times 0 and y. So the second eigenvalue is equal to 1. So basically, you're looking at the reflection of the vector on x-axis and on y-axis. So the reflection of x and y on x-axis is x and 0. The reflection of x and y on y-axis is 0 and y. So that's how you could divide this up into two vectors, x and 0, which is basically this vector right here, and 0 and y, which is this vector here. It makes it much more easier to find the eigenvalue for each vector in the plane. So basically, when you're trying to find the eigenspace of lambda, you're basically saying that, hey, I'm taking all of these vectors, x and 0, along with the 0 vector, which is going to be the eigenspace for -1, and the eigenspace for 1 is going to be the collection of all vectors, 0 and y, along with the 0 vector. So the eigenvectors corresponding to lambda 1 equals to -1 are the non-zero vectors on x-axis, and the eigenvectors corresponding to lambda equals to 1 are the non-zero vectors on the y-axis. This implies that the eigenspace corresponding to -1 is basically your x-axis, and the eigenspace corresponding to 1 is basically your y-axis. It includes the zero vector as well.